In this video, I want to show you how we come up with the probability of colonization, but I want to recap just a little bit, because in the qualitative risk assessment, we had the probability of a pathway times the probability of arrival times the probability of passage times the probability of colonization times the probability of spread. And so far, we will have accounted for all of these things up to and including the probability of colonization and spread by the time we finish this video. But pathway probability is a 1, that's clear. The probability of arrival has been captured, and we're going to return to that in just a moment. That's been captured in this information. When we look at passage, we looked at passage as the number of fish, and we began to move to the probability of colonization by comparing the sum of the fish to the number of fish required to see whether we had colonization or not. So now what we want to do is combine these colonization probabilities for all the different population sizes. Here's how we're going to do that. We're looking at this little square over here to the right, and you'll notice this first variable is population size. So I want you to see what that variable is. This is just a discrete probability distribution, and notice here is 0, and 0 goes up to 50%. That's the same as we have in this value right here. We have 1, that goes up to 40%, the same as this value. 2 goes up to 8%, and that's this, and 3, of course, is 2%. So in other words, this distribution here was constructed using these weights that our expert gave us for the year t0. So here's what happens. We have a distribution in here, and when I hit the recalculate button, you can see sometimes it's a 1, sometimes it's a 0, a 2, and 2% of the time it will be a 3. So the way this works is we calculate a population size. Here it's a 2. When it's a 2, that means we go over here to the medium population and look and see what is in the colonization cell. In this case, it's a 1. So that 1 is copied here. Okay? So now here's my second iteration. The population size is 0. That means there is a negligible number of fish that have arrived at Brandon Roads, and so we automatically know that will be no colonization. So a 0 goes here. There's another iteration. It's a 2 again by chance, and we go back over here, and once again 2 is a colonize. So we copy that number. So what's going on in this cell here is the population size is simply directing us to choose whether we will use this value, or this value. Whoops, excuse me, this value here. So I did this simulation 10,000 times. We collected this number here 10,000 times. Here, let me do 1,000. We have to do a little bit more than 100, but let's do 1,000 here, and I'll show you how this works. So what this is doing is it's taking into account the different population sizes that we could have. And it's essentially using that 50, 40, 80, 8, and 2 as weights. So here we see a minimum of 0, a maximum of 1, and an overall probability of 0.0680. In my earlier simulation, I used 10,000 iterations, and I got a probability of 0.0755. Calculating the standard error for that proportion, I have a distribution much like you saw in the last video. I know it's a normal distribution because we have a very large sample size. I know its expected value is 0.0755, and its standard deviation is the standard error. So this is a sampling distribution. This value here 0.0794 is the realization of the moment. And if you look up here, 0.0794, that's the same thing. All this does, if you look in the formula bar, is it says whatever this value is, take it and put it here. Now we have one other value in yellow that we elicited from our experts. And here, when I put together this dummy model, I just used a PERT distribution. That would be changed to a beta. But for now, notice that this says the minimum probability of spread given that we have colonization is 0.6. The maximum probability of spread given that colonization has taken place is a 0.89, and most likely it's going to be a 75% chance. So you see here, this number includes the existence of the pathway, the arrival of a population, the passage of fish through the system, and colonization. So it has those same four elements that we had in the qualitative risk assessment. They're handled a bit differently here, but they all get rolled up into this probability of colonization. So when we multiply this times this, we get a probability of establishment of 0.05. And we've done the same thing for year T10, same thing for year T50. So we just did a simulation of 1,000 iterations. Let's take a look at our results here. This is showing us the results of 1,000 estimates of the probability of establishment. So we don't know what this number is. We would use a 5-number summary to summarize it numerically, or we could use graphics to do that. But let's compare this to the probability of establishment by year T10. And here you see our probability of establishment by year T0. The probability of establishment by year T10 is considerably greater. We'll add the probability of establishment by year T50, which would be the value of greatest concern, I suspect, for decision makers in a planning study. And you see the third distribution here. Now, the way this model would work is, as seen, we have the probabilities of establishment for the without project condition. We would want the with project condition. These values would not change unless there were specific measures that were going to be taken that would make a medium or a large population less likely. So if there was an intensive effort to fish out the Asian carp downstream of Brandon Roads, then perhaps these weights would change. But for simplicity, we're going to assume that they stay the same. The number of fish that would pass through the system, this is the value that would change. This would change this would change, and this would change. So we would have, presumably, instead of the distribution that we have here, 0, 2, 6, and 10, if we had an additional electronic barrier and CO2 bubble system or something like that, our experts would perhaps then say, okay, well, maybe it's a 0 and the maximum might be 4. And the 25 percentile is also a 0, and maybe this is a 2, or something like that. But these numbers here would be reduced. When these numbers are reduced, these sums will be reduced. This number would remain the same, but what would happen is the probability of colonization would be reduced. And so that's basically the way this model would work. What you've seen let me go back to this output here. This would be the output for the without project condition from one expert. If we use 5 or 6 experts, we will have 5 or 6 such sets of distributions. So combining them, communicating that information, doing that sort of analysis will take a considerable amount of effort. But at this point, hopefully you would understand how this quantitative risk assessment estimate is moving forward.